This video was sponsored by Brilliant. In 1999, during the development of Quake 3, id Software once again pushed the boundaries of what game engines could do. Quake 3 was a demonstration of elite software engineering. The fact that games like Half-Life, Call of Duty, and even the GOAT Daikatana have their roots in the id Tech engines shows just how massive its impact has been. Quake 3 wasn't just a fast-paced arena shooter, behind the curtains it was a Mona Lisa. While most games were still figuring out the basics of multiplayer, id Software was implementing virtual machines, a unified event queue system, client-server architecture, prediction, and even a sophisticated bot system. This wasn't just game development, it was software engineering at a whole different level. And that's exactly why Quake 3 is still worth studying today. This is the last part of a 3-part series. I walk through source code of 30-year-old game engines, analyze architecture, the code, and search for universal lessons. This is Quake 3. As you know, my videos have no filler material, so be ready for almost an hour of real content. During the preparation of the video, I read Masters of Doom, JMP van Waveren's thesis on the Quake 3 arena bot, Fabien Sanglard's Quake blog posts, and a lot of other material. You can find all the links for the resources in the description. Now, before I start, let's go through the roadmap of the video. This video will be even more technical than the first 2 parts. And if I got anything wrong in the video, don't hesitate to correct me in the comment section. So, first we're gonna start with the architecture, the black box and the white box, then we're gonna go through the main loop where I will also talk about the event queue system, then we will dive into the virtual machines and system calls, then I will talk about the bot library, fuzzy logic and genetic algorithms, and last but not least comes the conclusion. Okay, so let's talk about the Quake 3 architecture. The Quake 3 project is made out of 8 projects. We have the botlib, cgame, game, Q3 UI, Quake 3, renderer, splines, and UI. Important to mention that the splines is not used anywhere, okay? Now, as you know, I like to start by looking at the whole project as a black box. So we have Quake 3 as a black box, and then we have some inputs and some outputs. Now, what we also know is that Quake 3 is a game and it gets player input via keyboard and mouse, for example, and we know that the output is manifested on a screen. So we can draw as input keyboard, mouse, player input, and as the output the screen. And as Carmack likes to say, there are 4 principal inputs to a game: keystrokes, mouse moves, network packets, and time. What we also know is that Quake 3 is an online multiplayer game and that the networking is done via UDP. So let's draw a UDP in and UDP out for the network communication. Okay, this is a very high level view. Now let's take a look under the hood of this black box. We are still staying on a high level perspective. We are not yet talking about bits and bytes, okay? We will start with the common part of the engine. So Quake 3 gathers all the inputs and translates them into events, and then puts these events into an event queue. These events are also stored in the event journal. We will talk about that in a minute. Okay, now besides this common part, the event system, Quake 3 is split into a client and server part. Now, the server side contains one virtual machine or VM, namely the game VM, and the server side has the authoritative game state and is linked against the bot library. The client side, on the other hand, contains 2 virtual machines: the C game or client game and the Q3 UI virtual machine. Also, the client side does the client side prediction and is linked against the rendering library. So from the server side we have the output of the authoritative game state to the clients, and from the client side we communicate to the server and the rendering output to the screen. During the video I will talk about the details and source code of the event system, virtual machines, bot library, fuzzy logic, genetic algorithms, and so on. So let's start with the event system. Now, the event system in Quake 3 was something new compared to its predecessors, Quake 1 and Quake 2. In the engines before, there was no unified event pump system, so it wasn't like all the incoming events go to a unified event queue and then the events are handled one by one. We can read about the making of the Quake 3 event system in Carmack's plan files. He says that the event system change was supposed just to clean things up, but ended up having a much bigger positive impact on the project. Ever since Doom, id Software developed the games with portability in mind, so porting to a new platform always involves having a way to display output and a way to gather all the relevant inputs. So all these inputs were taken in different places. So you call the function send key events once every frame, and it would then go through whatever it needed on a system level and call back into game functions like mouse moved, for example. Now for Quake 3, Carmack started reevaluating this concept, so he came up with the idea, why not create a unified event system that gets all the events and puts them into a single event queue. His original vision was just cutting down on the required system entry points, but it turned out to have other major benefits. For example, if all events are coming through the same point, it makes it very easy to create an event journal, which basically records everything the game received. That means, on the other hand, if you encounter a bug, you can easily reproduce it, since you have the whole record of events that happened before the bug. And this is very important for bugs that happen rarely and seem not to follow a pattern. Now listen, this is what elite software engineers do. Every time you develop something, or let's say before you even start developing, it makes sense to also think about, how am I going to troubleshoot this if it's not working as I expect? I know there's test-driven development, but that's not what I'm talking about. Test-driven development can be good or okay, but it will not prevent Heisenbugs. If you don't know what Heisenbugs are, a Heisenbug is a bug that seems to disappear or alter its behavior when you try to study it. And that's why it's good to have sometimes a way to trace back everything that happened before the bug. So when developing a system, think about a way to create traces like event logging, log management, input tracing, and so on. Let me quote Carmack. Key points for this journaling was that journaling of time with other inputs turns a real-time application into a batch process, with all the attendant benefits for quality control and debugging. So with a full input trace, you can very precisely play back the whole session to any point, conditional breakpoint on a frame number, or you can play it back at any speed while also covering the exact same input code path. And as he says in his plan files, this approach seems to be obvious to be the right one to do. But now my 2 cents. Everything looks easy when you get the solution presented. It reminds me when I was studying for my math exams, every time I couldn't solve some equation, the moment I opened the solutions, everything looks so easy and obvious. Now let's see how this looks like in practice. So in my opinion, the best way to understand this event queue is to go through the main function. Okay, so the main function for Windows is located in code, win32, and then winmain.c. Just like in the other games, it starts with initializing a bunch of stuff like cominit, netinit, and then we enter the main loop. This is where the event queue gets loaded with events. So if you go, for example, in input frame, you will see we have functions for input joystick move, input startup mouse, move mouse, activate mouse, and so on. Now if you take a look at this input joystick move function, you will see that it basically reads the buttons, and at some point we do this system queue event. Now we can also take a look at this function, and if we go in there, we can see how does this system event even looks like. So we have event time, type, values, pointer length, and a pointer. Okay, but now let's go through the mechanics of the system event queue function. This function queues up an event for the engine to process later. It could be anything, mouse input, keyboard input, network packet, doesn't really matter. Every event gets funneled through this unified system. Okay, so let's break down the function sysqevent. First, we create a pointer to a sysevent struct. Then here we are assigning the address of an element from this array to the pointer. This allows Eevee to point directly to that memory location, okay? Now event queue is an array of 256 elements, which is defined somewhere above. Okay, yeah, here. And this stores all the events. Now, event head is the index where the next event will be written. And event tail is the index where the next event will be read. So if event head equals event tail, the queue is empty. And if event head minus event tail is greater or equal than max queued events, the queue is full. this event head AND operator is a bitwise AND operator, so mask queued events is a bit mask used for wrapping the index. And this is a common ring buffer trick, assuming its size is a power of 2. It basically picks the current head position in the queue. So now EV is pointing to one of the elements in the array. Okay, now if the number of the queued events equals or is greater than 256, that means that the ring buffer is full. And we are about to overwrite an event that hasn't been processed yet, and that's generally speaking bad. So it prints a warning, overflow. And now what they have to do is to free the memory. We are in C, remember we have to take care of the memory. If you end up missing this bug, it will be very hard to find it later on. So what this does is it checks whether the event we are about to overwrite is a dynamically allocated data pointer, and if it does, it frees that memory. By doing it that way, you don't leak memory when discarding old events. Okay, then they increment the event tail. This effectively drops the oldest event and frees up one slot in the queue. After handling that, they increment the event head. Now, event head points to the next write slot for the following frame. Then, if time is 0, they set it to the current timestamp. Okay, when all of that is done, then it's time to write the actual event data into the queue slot. And that's it. The event is now sitting in the buffer, ready for the engine to process it. And that's how this circular buffer works. Fast, simple, and because of this overflow check, very safe. So all incoming input, keyboard, mouse, even network packets flow through this function. They get converted in a sys event and then processed frame by frame. It's one of the code sections that don't get the attention they deserve. It's the quiet hero of the Quake 3 engine. Okay, so that's how the event system works. Very elegant. So when designing the system, you should also think about integrating something like this in your software. As I mentioned before, a unified event system gives you the chance to easily create an event journal containing the full record of events. And I'm not saying copy-paste this one-to-one, but the idea per se is very valuable. I mean, I would like to have something like this when I'm going out with the boys. I could pinpoint the exact moment where things started happening, that tipping point, and maybe recreate some situations only for further research, of course. Anyways, that leads us to our today's sponsor. Brilliant is like a gym for your brain, except unlike your gym membership, you'll actually use it. Instead of going through an existential crisis during the meetings, you can take the 5 minutes and turn it into actual progress. Logic, algorithms, neural networks, quantum computing, it has everything. Clean visuals, clever pacing, and just enough difficulty to keep you going. The Brilliant app makes it easy to learn anywhere. On a plane, on a boat, of course if you have one, or while you're waiting for my new video to come out. Click on the exclusive link in the description or scan the QR code on the screen to try everything Brilliant has to offer for free for a full 30 days. That's definitely longer than your last relationship, and this one actually teaches you something. You will also get 20% off an annual premium subscription. No questions asked. How about that? Now back to the video. But now if we go back to the main loop, we will see that the engine is not calling the renderer directly from the main loop. So let's dig deeper, and that will lead us to the next topic. Okay, so we have COM frame, then the COM frame calls the server frame, but that's not the one we are looking for. We are looking for the client frame, since the client is linked against the rendering library. Okay, here we go, CL frame, client frame. And here we can see a VM call, that's what I'm looking for. Now, what is happening is the engine is communicating with the VMs via these VM calls. So let's talk about the virtual machines in Quake 3. And this is gonna get kinda complicated, but this is a C code review video and not, I don't know, what if Linux distros had personalities video. I promise, I will start simple as possible so even prompt engineers can learn a thing or two today. Okay, so generally speaking, when most people hear virtual machine, they are thinking about something like VMware, VirtualBox, and maybe even some are thinking about BlackBerry QNX. Basically, where we are emulating a whole system with its peripherals. That's hardware level virtualization. Now, Quake VMs are something different. You're not emulating the hardware. The VMs in Quake are used to isolate the game logic from the engine, sandboxing it. First, we will take a look at the VMs from a top level, and then we will get into the mechanics, into the code. So in order to easier understand this, let's first take a look at the architecture diagram. So in Quake 3, you have the following three virtual machines. On the server side, we have the game or server game VM. On the client side, we have the client game VM and the UI VM. But how do we get there? How is the engine compiled and how is the VM compiled? Okay, so first we have the Quake 3 engine source files. These are compiled to the Quake 3 executable. For the virtual machines, we also have dedicated source files. These .c files are compiled with the little c compiler, LCC, but they are compiled with a special compile configuration, so the compilation process doesn't deliver you the Windows portable executable. Instead, you get the intermediate representation, the object file with the text-based stack machine assembly. Then, an id software tool called Q3ASM.exe takes all these text assembly files and stitches them together into a QVM file. In the process, it also does some other stuff like transforms everything from text to binary or gives system calls a negative symbol number. And then when loading the bytecode, Quake 3 converts it to x86 instructions. Now, besides the virtual machines in the QVM format, the Quake 3 engine can also use native DLL files instead of QVM files. I will talk about the difference in a minute. Now, to give you a rough idea, I will walk through the example that Fabien provided in his review. So let's assume we have this source file and we want to run it in the VM. First, we translate it with LCC. We will get this object file. So data, initialize variables, code or text, and then come the uninitialized variables. The functions are defined in this pros and pros sandwich. This is a stack machine. Everything is done on the stack, with no assumptions about the CPU registers, okay? Now, for each .c file, we get this object file. And then the Q3ASM creates the QVM from all these object files. Okay, so that are the basics of how the VM system is structured and generated. We have the engine, it gets the QVM or DLL files in a specific format and then it reads it. And now you're probably wondering, or maybe not, why would anyone do this? What is the actual benefit of such an approach? I mean, besides being a huge flex of putting a virtual machine inside a game engine, technically speaking, I mean. I mentioned the answer already in the beginning. Introducing the VMs and not doing everything directly in the engine gives you an isolated environment. So you're providing the game logic access to the engine only through controlled system call interfaces. The game logic cannot do whatever it wants, but only the things that are allowed via these defined interfaces. And by doing it this way, you are lowering the possibility to crash the whole engine with a game mod, or to manipulate any engine mechanic or even cheat. And this is the idea, and I mean, I'm pretty sure that some people manage somehow to circumvent this and still crash the game or cheat or whatever. But we are talking now about the general software architecture concept of isolating a specific part of a software and providing only specific interfaces to it. So we are decoupling the engine from the game logic. This is elite. So the game logic sends a request for a system call in the engine. The engine receives this request and does the system call. Remember, it can only call for the provided system calls. The other benefit is that the mod is platform independent. That means you can create a QVM file, a mod, and you can run it on any platform supported by the engine. You don't need to do anything platform specific. But now, I don't want to leave it just like that, so let's walk through a high-level example of how this works. Okay, so the engine calls VM call with the VM and function number. The VM call decides how to execute the VM based on its type. And now we have two options. First, if the VM is interpreted bytecode, a QVM. So if it's a QVM, VM call calls VM call interpreted, which setups the VM environment, the stack and registers, and starts the bytecode interpreter. The interpreter executes that instruction and calls VM system call with the syscall number and the arguments. And then the engine handles it via dispatcher. Now the other option is if the VM is a native library, a DLL. Then VM call directly calls the VM main function exported by the DLL. The VM logic runs as native code and calls a trap function. The trap function calls syscall with the syscall number and the arguments. This is a function pointer provided by the engine, and again the engine handles it via dispatcher. So both paths end up doing the same thing, sending a syscall number and arguments into the engine which dispatches them. But QVMs do it via interpretation and DLLs do it via direct function calls through a function pointer. Okay, now let's dive into the code. So let's say we want to render something. The engine's main loop reaches a point where it needs to render a frame. So it calls com_frame. Inside that it runs client frame, which eventually leads to screen update screen. Which calls screen draw screen field, which then has a switch case that leads us to client game rendering. At this point the engine needs the client game VM or cgame to do its part in drawing the frame. So it calls VM call client game virtual machine client game draw active frame. This tells the virtual machine run your function number cg draw active frame now. Here cgvm is the handle to the cgame module and cg draw active frame is just a numeric constant. This is defined inside the VM as an enum, which maps to the start of the function that performs the draw logic. Now, here is where it depends on the kind of VM you're running. If the VM was loaded as a native DLL, then VM call would just call into the exported VM main function from the DLL file. If it's a QVM, it runs the VM call interpreted, since we want to interpret bytecode. Now, first we will go through an example where the VM is in the form of a QVM, so where we interpret bytecode. In that case, VM call internally delegates to VM call interpreted. Now, VM call interpreted is the function that handles execution of bytecode VMs. It is defined in vminterpreted.c, and this is where the actual QVM interpreter starts up. So what it does is, sets up the VM's registers and stack, resolves the function address from the symbol table using the enum, and then jumps into the bytecode execution loop. Before the interpreter executes any instructions, it prepares the virtual stack, kind of like what a real CPU would do before entering a function. So the Quake 3 VM keeps its own internal stack in memory, and it uses a software emulated stack pointer to track the top of the stack. At the moment of a function call, the stack might look like this. So this layout stores everything the interpreter needs: arguments, locals, return info, even space to write the return value later. The first instruction executed is usually op enter, which acts like a function prolog in assembly. It setups the frame pointer and allocates space for local variables by adjusting the stack pointer. From here on, the QVM runs instructions one by one, basically simulating a stack-based virtual machine. Internally, it uses a program counter, stack pointer, and a frame pointer just for debugging. Now, inside the VM, execution reaches the compiled version of the cgDrawActiveFrame function, which is defined in the cg_view.c. It is compiled into bytecode using the Q3VM toolchain that I've shown before. Let's say it wants to print a message or start a sound. The problem is the VM is sandboxed. It can't just call engine functions directly. So instead it performs a syscall, a numeric request to the engine. So the runtime syscall flow looks like this: QVM bytecode, interpreter hits syscall instruction, VM system call, engine dispatcher. Now the engine function responsible for handling syscalls from the client game VM is CL cgame system calls, which is defined in CL cgame, which is client game.c. It looks like this. We basically have a switch case here. So the VM sends a syscall ID and arguments, and the engine dispatches it through a big switch statement. This is how the sandboxed QVM code asks the engine to do things: print, render, start sounds, and so on. Now let's contrast that with the native DLL VM case. Before we continue, if you like the content, hit like and subscribe. Last time only 5% of my audience was subscribed to the channel, and now we are at 5.6, baby. We are so back. I want you to know that your support helps me immensely to make better content. So I want to take the chance and say a big thank you to my Patreons and YouTube members: Viorel Petku, David Ziskovski, Joey Herschel, John Stanovic, Amro Ibrahim, Dr. Slowdev, Luis Aruda, Joe Williams, Peter Iskandar, Noah Cope, and Alex Grew. If you wanna support me get better equipment, you can become a Patreon or YouTube member. The link is in the description. In DLL builds, we have these trap functions, which use the function pointer syscall. So when the engine loads the DLL, it calls the DLL entry function. This assigns the syscall function pointer to the engine's dispatcher. Same CL cgame system calls function. But in the DLL case, we have these trap functions. So now every trap call is routed through. The trap function calls the syscall, then comes the engine dispatcher, and then the real engine function is executed. That means that the QVM and DLL modes both end up doing the same engine syscall handler, but the way they get there is different. Now let's talk about this weird looking function pointer. So we have static int QDECL syscall int arg int QDECL blah blah blah. This is a nightmare for any Python developer or prompt engineer or vibe coder or whatever it's called this week. Now this on the right side is not a real function address, it's what we call a sentinel value. It casts a -1 into a function pointer, which gives you 0xFFFFF, an address that cannot be executed. The point of this is the fail-fast safety. If the VM tries to use syscall before the engine assigns it properly, the game will crash immediately, loudly and obviously, instead of silently corrupting the memory. Later on, when the engine loads the VM, it sets the actual dispatcher, syscall equals system call. And from that point on, all calls from the VM to syscall are routed correctly into the engine. This use of this -1 as a sentinel value is a classic C pattern. Unlike null, which might be handled quietly, -1 ensures a hard crash and makes debugging uninitialized pointers obvious. Now you may be wondering, what is this QDECL type thing here? QDECL, I don't know if I'm pronouncing it correctly, but let's call it QDECL, is just a macro that defines the calling convention, and in Quake 3 it expands to __cDECL. So why does this matter, or what even is this? So when a function calls another, it needs to pass arguments, usually by pushing them onto the stack. After the function returns, someone has to clean up that stack space. If the caller and callee disagree on who should clean up the stack, you're in for crashes, corrupted memory, and similar type of events. So a calling convention defines how arguments are passed on the stack or in registers, in what order, left to right or right to left, who's responsible for cleaning up the stack, and which registers must be preserved. Now you have a few common ones like cDECL or statcall or fastcall, but Quake 3 uses cDECL via QDECL, and here is why. cDECL is safe for periodic functions like syscall in this case, because the caller knows how many arguments were passed. It works reliably across binary boundaries, like when a VM calls into the engine via function pointer, and it avoids stack cleanup mismatches between the modules. So if the VM thought the caller should clean the stack, cDECL, but the engine was using statcall and already cleaned it, the following would happen. You would have a double cleanup, stack pointer goes out of sync, you would have return addresses corrupted, and you would have a crash. Now, by having both sides use the cDECL, everything stays consistent. So you have on the VM side QDECL, which is then a CDECL, and on the engine side you also have QDECL via system call. Now by doing it this way, everyone agrees on how arguments are passed and who cleans up. This is very important, knowing who will clean up the mess. And that's why QDECL matters, okay? It's not just a macro, it's what keeps this cross-module syscall interface from collapsing. Now you have to understand that this is not something you come up with and code it during lunch break. So in case you're overwhelmed by all of this, it's completely understandable. But it just shows how much details and everything they put into this. And that's why, in my opinion, this is peak software engineering, or you can call it elite software engineering. And I'm also not calling this coding, this is software engineering. Now, this concept is very common in safety critical software. You don't want your application layer to be able to crash the whole system. Also, a common thing to do is separating the safety application completely from the, let's call it, user application or consumer application. And then running the safety application even on a separate core if your hardware allows it. This, of course, introduces some overhead like inter-core communication, but generally speaking, you can't crash the safety application with a dysfunctional user application. Now, in case you feel bad about yourself, about your education and maybe career and job, you can read Carmack's plan files and make it even worse. On August 26 in 1999, Carmack wrote that he wrote a Hello World example for this VM concept in a day. Let that sink in. Let's talk about quitting. Okay, enough of the virtual machines, now let's talk about the bot library. First I wanna say rest in peace to the author of the botlib, JMP van Waveren. Now, there is an interesting story about the development of the bot library, and this is a small quote from Masters of Doom. To make matters worse, a fundamental ingredient of the game, the bots, was missing. Bots were characters controlled by the computer. A good bot would blend in with the action and flesh out the scene like a robotic extra, as well as interact with the player. For Quake 3, a deathmatch only game, bots were essential for single player action. They were implicitly complex because they had to behave like human beings. Carmack had decided for the first time to delegate the job of creating these bots to another programmer in the company, but he failed to follow up. Once again, Carmack incorrectly assumed that everyone was as self-motivated and adept as he was. He was wrong. When Grammy struggled to rein in the work, it was discovered that the bots were completely ineffective. They didn't behave at all like human beings. They behaved basically like bots. The staff began to panic. By March 1999, they had a reason to be scared. So then they decided to let JMP aka Mr. Elusive to do the botlib, who by the way was also the author of the Omicron and Gladiator bot from the previous games. Carmack also said on Twitter that he was the best developer he ever worked with. Imagine the goat saying that you're the best developer he ever worked with. I mean, now JMP van Waveren has also published his thesis on the bot library from Quake 3. I will provide a link in the description. And I highly recommend reading it. It is very well written and easy to follow. It starts by defining the goals and requirements for the bots, then he talks about the technical stuff that has been used, and then he breaks down the bot library step by step. You have to keep in mind that this thesis was published before the source code was open sourced, so we'll not find for every feature one-to-one references to the Quake 3 code in it. Now I'm gonna talk about how the bot library works, and then we're gonna take a look at the code of the fuzzy logic, genetic algorithm, bot characters, and so on. Okay, so the Quake 3 bot system builds upon the Gladiator bot system from Quake 2, which by the way was also done by JMP. In the Gladiator bot, the bots didn't just have different names and looks, but also an own playstyle, which was achieved by parameterizing the fuzzy logic differently for each bot. So for each bot, a set of fuzzy logic parameters had to be stored. Okay, now let's first start with the bot architecture. Van Waveren decided to use a layered architecture for the bot logic, so we have 4 layers. The awareness input is derived from the lower layers, and the decisions from the higher layers are executed through the lower layers. So at the bottom we have the first layer with the awareness system and basic action. Then we have the second layer with the components fuzzy, character, goals, navigation, chats. Then the third layer with MISC AI, AI network, commands, and at the top we have the team leader AI. The first layer is the input and output layer for the bot. The area awareness or AS provides the bot with all the necessary information. The AS provides necessary information. Focus, bro, we have things to do. Okay, so all the quote senses come from the awareness system. All the actions are then done via the basic actions. The second layer provides something like a subconscious intelligence. This includes the fuzzy logic for selecting goals, navigation towards a goal, the logic to interpret chats, and the functionality to store and retrieve bot characteristics. The third layer is a mix of if-then-else rules and an AI network with nodes for different situations. Something like a state machine. This dictates when should the bot fight, when should it run away, and so on. The fourth layer is the team leader, or command center as Van Waveren calls it. In each game, one of the bots is designated to be the team leader. The team leader organizes the team. Now the whole logic runs in small time steps. So the bot's brain, so to speak, operates at 10 Hz. So every 10th of a second, the bot checks his status, evaluates the situation, and decides what action to take. And it uses the area awareness system to stay up to date with the world. Now let's take a look at the information flow between the layers. So all the arrows that go upwards represent the flow of information about the bot's status and its environment. And all the arrows that go downwards represent the decision that resulted from the bot's thinking. We also have communication between the components within the same layer, which is not visible in this diagram. So the code at the higher levels requests information, processes it, makes a decision, and communicates that decision to the lower layers. Now let's take a look at the bot library in the context of the software architecture. So we have the client, we have the server, and the game virtual machine which communicates with the bot library. So the game communicates with the first and second layer of the bot library, and these two layers then communicate with the third and fourth layer. The client module is where the player input and output happens. Back to the bot library, so the area awareness system provides the bot logic with all the information about the environment. This is the longest chapter in the thesis, and covering the whole thing is way beyond the scope of this video, but I will give you a brief overview. Okay, so the area awareness system is the whole system that provides information about the environment. This includes navigation, routing, and other entities. In Quake 3, the area awareness system divides the game world into 3D regions called areas, where movement inside each area is simple, like walking in a straight line. The system pre-computes reachabilities between these areas, meaning it knows in advance how a player or bot can get from one area to another. That this can be walking, jumping, climbing, etc. Bots use this data to quickly plan paths through the world without doing expensive real-time calculations. Now, in Quake 3 we have this BSPC tool that is used to create AIS files from BSP files. An AIS file is a file with areas used by the Quake 3 Arena bot in order to navigate and understand a map. The Quake 3 Arena maps are stored in the BSP files. Now, as I said, you can't just define areas, you also need to define the reachabilities between two areas. In Quake you have 12 types of reachabilities. For example, swimming, walking, jumping, crouching, teleporting, using an elevator, and so on. Now these reachabilities are then calculated for each area, and then they link from one area to another area. Okay, then we have bot actions. When humans play Quake, they use their keyboard and mouse to perform actions. These inputs are then translated into actions. But the bots live in the game, so to say, therefore they don't need physical devices like keyboards. So they just generate these inputs based upon the decision-making algorithms. And bots can choose between several actions like attack, use an item, jump, crouch, move, and so on. Then bots also have characteristics, so anyone who played Quake 3 with bots knows that different bots behave differently. You have a set of characteristics, which are values in a specific range. And a good bot is not a bot who is unbeatable. A good bot is a bot that makes the game fun to play. Yes, of course, if someone wants to train, I don't know, for some specific reason, it makes sense creating a high-skilled bot. But generally speaking, you want a bot that behaves like a human and makes mistakes. These characteristics drive later on the decision making of the bot via the fuzzy logic. Now let's talk about the fuzzy logic. So fuzzy logic is a form of logic that deals with reasoning that is approximate rather than fixed and exact. Where in traditional binary logic something is either true or false, a 1 or a 0, fuzzy logic allows values in a range. So things can be mostly true or mostly false or somewhat true, and fuzzy logic is used everywhere. Most household electronics are using some kind of fuzzy logic. Now let's go through a small example of fuzzy logic. Imagine we have an air conditioning fan and we wanted to have variable fan speeds based on the room temperature. If it's cold, fan speed is 0, if it's warm, fan speed is at 50%, and if it's hot, fan speed should be at 100%. In between, we want to blend the values by using fuzzy logic. So now, for example, let's define a temperature value at 25 degrees. Then we start defining the membership functions for the temperatures. For cold, we have this. For warm, we define warm. And for hot, we define what does hot mean. And then we need some defuzzify logic. In this example, we will use the most simple weighted average. Okay, then we go to the main function and then we define the variables for cold, warm and hot and call the corresponding functions. And after that, then we run the defuzzify logic function with these variables. So the idea is to take input parameters and then make a weighted decision based on these parameters. That gives you the option to create a more sophisticated decision making for the bots compared to just a if else true or false. Sometimes a bot wants to pick a weapon and fight, but then the input parameter like low health indicates to the bot that it's better to avoid the fight and run away and look for health packs. So it's telling the bot not only if it wants to do something, but also to what degree do we want to do something. It's like you want to become a good C programmer, but to what degree do you really want to become a good C programmer? You get the idea. So the bots get all the input parameters of the current state of the environment and its own state and then decides based upon the fuzzy logic what to do next. The input parameters can be, for example, what items does the bot currently possesses? How much ammo does it have? How much health, armor? Then it can also evaluate situations like how far away is the enemy and then make a decision on what weapon to pick based upon the distance of the enemy. So as you see, the Quake 3 bot system does not use neural networks. This fuzzy logic system also gives you the option to parameterize each bot differently with limited amounts of memory. Now if you go to the source code, we can see that the file b_ai_weight has the functions for reading the fuzzy weights. These are basically functions for reading all the fuzzy weights in a particular format, which will then be used in the actual decision-making functions. For example, we have a bot choose best fight weapon. Here you loop through the weapons and then update the best weapon based upon the fuzzy weights. If you take a look at this example from his thesis, he talks about the lightning gun. How the fuzzy logic weights the decisions based on the enemy distance, for example. The max range for the lightning gun is 768. If it's within the range of 768, then the bot looks at the ammo. If it has the ammo, then the bot's preferences for the weapon, so to say, increase. But if the enemy is beyond this range, in this case 800, then the preference drops to 0. Okay, now let's go back and take a look at the source code of this interbreed fuzzy separator function. Okay, and this looks like a copy-paste error because we have 2 times the same fuzzy separator fs2 in here. And generally speaking, this function it's not randomizing anything, it just seems to be averaging the values out. Okay, so that are the basics of the bot system fuzzy logic. I know many people, myself included, thought that the bot system uses trained neural networks to create these bot behavior patterns, but that's not the case here. The author also said that training neural networks would have taken huge amounts of resources and time, which I agree, and I also had a similar situation like 8 years ago. We were developing a prototype, a proof of concept, EMG controlled interface for an arm prosthesis. So we wanted to use these EMG sensors to read signals from the arm muscle, and then we wanted to use fuzzy logic to determine which hand gesture was the person attempting to make. Like, for example, is the person trying to make a fist or point with a finger somewhere or whatever. Now, the amount of time I had for this prototype was very limited. So I just made a proof of concept where I wrote a fuzzy logic algorithm. I measured the signals and parameterized the weight factors and membership functions. Then my fuzzy logic algorithm just read the values and determined which gesture it is most likely. The code was very simple, so I just read the data through TCP and then evaluated the data. This was basically done in a day. Training a neural network to do this would deliver better results, but the implementation and testing overhead would have been significantly higher, and we definitely didn't have the resources to do that. So in the end, it worked and fuzzy logic did the trick. Okay, now let's talk about the genetic algorithm which was used for parameterizing this fuzzy logic in the bot library. Okay, so what is a genetic algorithm? Genetic algorithms are optimization algorithms that have been derived from the process of natural selection in biology. The idea is, if you let evolution go for long enough, more adapted biological beings will eventually emerge. You can imagine it like if it is an advantage for a bird to be fast, to catch more insects, and eventually to outbreed the competition, faster birds will spread their genes more frequently and create a larger population with their set of genes. Here and there you will have few mutations which can positively or negatively impact evolution, but generally speaking that's the basic idea. Now if you put it in some more technical terms, you need the following: an individual with defined characteristics like size, weight, anything measurable, a population which is a group of individuals with a fixed population size. Then we need a fitness function which will help you rank all the individuals based on their fitness. We need a mutation rate which is usually just 1% or less, but you can of course crank it up if you want. Then we need a selection algorithm that selects two parents, so those with higher fitness factors should be selected more frequently for the breeding. Then we need some permutation logic, breeding logic, like how do we want to combine two individuals into a child? Do we just randomly exchange their characteristic values or add them up or average them out or anything else? And then last but not least, we need a random number generator. You can use of course true random or pseudo random, it is very use case dependent. I usually went for the Marseille twister RNG and for my use case it worked fine. Okay, so then the flow looks like this. First we generate a population. We use the RNG to randomize the characteristics of the members. Then we evaluate all the fitness values for each member of the population. Then we let a picking algorithm pick two parents. We pass the parents to the breeding logic. And the breeding logic then creates a child member. Now we keep doing this until we get a second generation of the population, okay? And while doing this, we want a 1% mutation in the children, so that after the combining of two parents, this can of course happen also before the permutation, we want one or more values of the characteristics to be randomized again. We want it to mutate. This is important because it gives you more variance during the optimization. Because solutions can quickly converge into local solutions instead of finding the global solution in the solution space. Now, I did a lot of work with genetic algorithms, and I also wrote a paper on genetic algorithms in the context of optimization of optical systems. Maybe at some point I can make a video about that. But now back to the Quake 3 genetic algorithm. So they used the genetic algorithm to get balanced fuzzy relations. So they generated bots, let them play against each other, ranked them afterwards, and kept creating new generations of the set. Now, if we take a look at the source code for the genetic algorithm, which is in BAIGen, we will see that they have only two functions. First we have genetic selection, and then we have genetic parents and child selection. Let's go through these functions. Okay, so genetic selection is a function that is supposed to pick a member of the population. So you have the number of rankings, so the number of members, and you have a pointer to the start of the array of the rankings. So first it starts adding up all the values. Okay, if a value is negative, it skips to the next iteration. That is what is continuous for. Then it goes to the next if. So if sum is positive, we enter this section. And then we set the variable select as random times sum. Okay, this is weird. So they roll the dice, get some random, but they never actually use it. So this might be some leftover code that has never been cleaned up, I assume. Okay, then we see this inverted roulette wheel selection. You subtract values from sum until you hit negative or equal 0 and then select that index, which basically means indexes with higher values have a higher chance triggering this condition. Okay, so now they also write a fallback where they use a random selection, and yeah, this basically guarantees that a member will be picked. And then we have this return 0, which is basically a safety net if none of this above works, which basically would indicate that something's wrong, then just return 0. Now, in my opinion, since I have some work done with genetic algorithms and hybrid genetic algorithms where I combined global with local optimization approaches to squeeze out even the last percentages out of the optimization, in my opinion, it would make sense to tweak this function a bit. Since, look, even though you randomize few values, you roll the dice, do some inverted roulette wheel, this is still a deterministic approach. And that's not really what you want from a genetic algorithm. The problem is this algorithm will always deliver you the same values if you use the same input set, same rankings, because you're not really using this random, this select variable or any other random. And also you will not come to this second part of the function because you will already hit a return before you even get there. So I don't really know how they used this function and created such good bots. Maybe they didn't even use this to generate the fuzzy parameters. The only thing I know is that when I played Quake 3 for the first time, which is, I don't know, it was in 2006, I thought these are the best bots I've ever played against. Okay, anyways, now let's go to the second function. So the second function starts with some checks to see if there are too many or not enough members of the population. Then the first parent is selected and the ranking is set to -1, and then the same thing is done for the second parent. This is probably done to mark which members have already been selected. And all of this is done on the local copy, by the way. Okay, and then they reverse the rankings and find the max ranked member. Okay, and then they select a child with the inverted rankings list. Now I'm not sure why they did it this way. Usually want to pick the best member and combine it with the best members. Maybe, and just maybe, so this is an assumption. Maybe if you pick the best of the best parents, maybe that would produce two strong bots, like an elite aimbot level bots, which would not be fun to play against, okay? So that's my only explanation why they do this reversing and picking and so on. And a general comment, I don't see a mutation factor in this genetic algorithm. And I also don't see the randomization of characteristics and so on. Probably it's not in this part of the source code, it's probably somewhere else. But as I said a million times, probably Quake 3 had the, in my opinion, best bots at that time. And I mean, Carmack said that JMP van Waveren was one of the best programmers he ever worked with, and that means a lot. I can only recommend reading his thesis. It's really well written, and it's about 100 pages, but it was a really good read. Now, besides the fuzzy logic and the genetic algorithm, JMP also explains the bot fighting logic in his thesis, which is very interesting. I'm not going into details, but he explains how the aiming, moving, and weapon selection works. Now, in order for bots to put all of this together, JMP created this central brain for the bots, which was the AI network. This is a diagram that shows how it works on a top level. So for different aspects of the bot actions, you have different nodes. For example, a bot activity over time looks like this. Now, it's important to understand that a good bot has to be balanced, so it has to blend in with players. And in my personal experience with Quake 3 was, they really blended in with the players. They even used chat, which was fun. I mean, different bots behave differently. I remember playing Quake 3 with my friend against bots, and he said something like, "I hate this bot." It was this ranger bot. He said something like, "He keeps killing me all the time." And I thought, come on, bro, as if it makes any difference based on the character, on the look of the bot. But during the last few weeks when I was reading this thesis on the bot system, I realized that my friend was actually right. So the bots do have different characteristics and they do behave slightly different, which honestly just made me smile. It also made me think about my friend. I haven't spoken with him in about 7 or 8 years. It's not that we are not on good terms, but it just happens that we both moved to different cities, and unfortunately I don't have his number or any socials. Now, some other honorable mentions from the Quake 3 source code are the rendering. Here I will link the shader manual PDF from id and the networking snapshots. I will provide a link from Fabien Sanglard's blog post about this. Conclusion. Quake 3 is not just a game, it's an artifact. A living fossil how big ideas drive engineering decisions. Nowadays, almost every company is trying to develop one product and then try to milk it into oblivion. No innovations, no big risks. Just try to find one thing and then let the marketing department try to get max profit without any new innovation. But this code base shows what happens when you don't gatekeep. When you don't lock your ideas in some corporate vault and just try to raise shareholder value the next quarter. Carmack wrote insane code, dropped the repo, made popcorn, and just watched the future unfold. That's how you move the industry forward. Openly, not by hiding behind intellectual property and copyright and subscription models. And that's what I love about these old id Software engines. They're not just functional, they're educational. They're raw and always honest. Every iteration, Doom, Quake, Quake 2, Quake 3, is an engineering response to a vision. And that is elite. Want modding to be easier? Build a VM system. Want pure multiplayer? Kill the campaign. That kind of courage is rare. Technically speaking, this was a very short period of time, but the leaps they made with each new engine were huge. I mean, id Software could have easily just do games with their existing engines and make profit, and not give out any source code away and not license their engines, but they didn't. And I don't know any other case in any other industry where something like that happened. Imagine a car company giving away their blueprints for their engines so people can just study them. Even the story of Daikatana, Romero trying to develop on the Quake 1 engine and port it later, just highlights how fast this tech evolved. It wasn't just version numbers going up, these were leaps. And yeah, I can't be totally objective. I grew up with these games. I didn't have a top-tier graphics card. I didn't even have a decent graphics card. But these games ran. That's why my friends and myself used to play these games long after their release. It always made me wonder how the hell they pulled that off. And all that memories are half the reasons I do these videos. And look, don't expect one-to-one reusability from this code. That's not the point. The point is to learn how others solved hard problems. You don't have to build an arena shooter in 2025, but you might need to isolate untrusted code, or build a plugin system, or just think differently. Good developers look at the system and ask, what can I steal? But great developers ask, what can I learn? That's the silver lining here. Now looking forward, I will keep doing these game code review videos, but I'm also thinking about reviewing non-game code bases. So if you have any suggestion what you would like to see, just let me know. You can leave a comment or you can shoot me an email. Or maybe I can do some embedded projects, showing some genetic algorithms, maybe coding a ray tracing physics engine, or maybe even reviewing some resumes. I could also do some code review of some of your projects, so yeah, just let me know. Okay, so that's it for today. If you like the content, hit like and subscribe, and see you in the next one. Tariq the next.